So we want to find the derivative and find all the critical points. So we need the derivative, then we need to set it equal to 0. So we have 4x cubed minus 6x. Before we set that equal to 0, I suggest factoring it as much as possible. Both of those terms have a 2x in common, so go ahead and pull it out. You'll be left with 2x squared minus 3. That piece can't really factor anymore. It's going to give us a pretty gross number, but that can't be factored anymore, so we have to leave it. I left my nice calculator in my office, apparently. I have to use the clunky one. So we have the derivative. Now we want to set it equal to 0. Since we have two pieces, we set each piece equal to 0. So we've got 2x equals 0 and 2x squared minus 3 equals 0. So we'll get x equals 0. And, whoops, x equals positive or negative square root of 3/2. But if I remember this correctly, oh, come on. There we go. This is approximately positive or negative 1.22474. Note that 1.22 is greater than 1 and negative 1.22 is less than negative 1. The interval we're working over is negative 1 to positive 1. So actually both of those two critical points aren't in our interval, so we actually don't need to care about them anyway. So that's nice. We now don't have to care about the nasty numbers. That is the one thing that I think we hadn't gotten to an example like that yet. But if your critical points are outside of the interval you're working over, you just don't care about them. But we do have one that is in our interval. It was x equals 0. And maybe I should note for people who are going to call me out on it. This derivative is never undefined. There's no denominators that we need to set equal to 0. So we're good to go. So remember, once you find your critical points, now it depends on what type of interval you're over. We're on a closed interval. So that's what I like to consider our nicest case. I think it's the nicest case personally. But if you have a closed interval, remember that's where you take the critical points that are in the interval. So we're only going to take x equals 0. And you take your endpoints and you plug them into the original function because you want to compare the y values. I have a new mask and I don't like it because it keeps falling off my nose. So we take all of those critical points and the endpoints that are in the interval and we plug them into the original function. So we've got x equals negative 1, x equals 0, and x equals... You don't have to list them in order. I just usually like to do it that way. So if we plug in negative 1, I should have figured out what these were before I started this. So that'll be positive 1 minus 3 plus 4. 5 minus 3 is 2. Y'all correct me on my arithmetic if I do something stupid. 0 to the 4th minus 3 times 0 squared plus 4 is just going to be 4. And then plugging in 1 will give you the exact same thing as plugging in negative 1 because both of those powers are even. 1 minus 3 plus 4 is 2. Once you have those, remember at this point you're just figuring out what's the highest number you got, what's the lowest number you got. Now notice here, the highest number we have is 4, but the lowest number we have is actually tied between the other two. But remember, it's perfectly okay to have multiple global extrema if they are at the same y value. So those are both actually going to be global minimums. So we will have global, I thought I switched back. Global max at 0, 4, and global min at negative 1, 2, and positive 1, 2. And remember, with these, you always want to list the x and the y value. So find your derivative, find the critical points, figure out what type of interval you're over. That's going to determine how you do the rest of the problem. If it's an open or closed interval, you do this process. If it's an open interval, so the only difference here, if this was an open interval from -1 to 1, but we didn't have the brackets, we had parentheses, what would happen is we would have a global max, but we wouldn't have a global min, because the global mins would have been at the endpoints. But if it's an open interval, they can't be at the endpoints. So if this was an open interval, if it was a completely different problem, the global max would still be at 0,4, but there would be no global min. Questions, concerns about this one before we go on to the next one? I'll hold on like 5 more seconds in case people are still writing something down. And then I'm going to switch back to the actual note page to do this last one, just so that it's all on the notes when I post them on Blackboard. So I'm going to jump back over to our notes, because that second one was technically finishing this last problem in the chapter 4 notes that we didn't get to yesterday. You know what I mean. Monday. Oh, there was even an extra tiny piece of hintness in this one. So we were asked to essentially maximize that revenue function. And so I noted the other day, apparently, I don't remember, that here we weren't explicitly given the interval that we were working over. We kind of had to figure it out via the context. But if we're talking about price can't be negative. Well, if you're trying to be a good business model, price is not going to be negative. It could technically be 0. That might be a little silly, but it could be. And then it can be as large as you need it to be. So the interval we're working over is technically 0 to infinity. When you have an infinity in either one of your intervals, in endpoints, it's going to mean that you need a number line. Is that a question or an accidental unmute? Going once, going twice. Okay. So we need a number line here. So, well, first, to have the number line, we need the critical points. So we need to find the derivative, set it equal to 0. Oh my. We need to find the derivative, set it equal to 0. So -12p plus 780. I don't know if 780 is divisible by 12, but this is a linear thing, so we don't really need to factor it much anyway. So we'll need to set it equal to 0. Solve for p. Whoops. Oh wait, it is divisible by 12 because this gives me a nice number. And we'll get p equals 65. This is never undefined. There's no denominators going on, so we don't have any more things we need to consider. But now we need to look at the number. Remember, the number line, the point of it is to make sure that global extrema can actually exist. Now, I know that with these contextual ones, it's usually just whatever the critical point is. I understand that. But you do always need to triple check that the extrema can actually exist. And especially if it's not a contextual problem and it's just a generic problem with a, infinity endpoint, you need to check. Now, since we're stopping at 0, I'm going to go ahead and remind myself not to go past 0. But I need some test points. So I don't know, 1, and I'm going to pick 100 because why not? But remember, the test points don't matter. You can pick whatever numbers you want. And since we're working on a number line, remember when you're working with the number lines, it has to be into the derivative. So we're plugging 1 into the derivative. We get -12 plus 780 is going to give us a positive number. I don't know what it is, but it's a positive number. Whatever the heck 780 minus 12 is. 768? I don't know. Sounds good. And if I plug in 100, we're going to get -1200 plus 780, which is going to be a negative number. So we're increasing, then decreasing. So what does that mean for the ends? That means we're going down forever in both directions. If we're going down forever in both directions, that means a global maximum can exist, which is good because we wanted the maximum. So we'll have a global max when P equals 65. Technically, in terms of answering that question, that was enough because they just asked what price should the company charge. So we could have just stopped at the 65, but I'm going to go ahead and figure out what the actual revenue is. I'm going to regret this because I have to use my clunky calculator. -6 times 65 squared plus 780 times 65 back into the original revenue function. So revenue at 65, we weren't actually asked for, but I found it anyway, is 25,350. So in general, if we were for some reason asked for the minimum revenue, there wouldn't be any, because the shape of this graph tells us that it's going downwards forever in both directions, so there can't be a lowest point. So Kayla, yes, for the number line, it's kind of like, remember when we were doing local maxes and mins, whenever you were working with a number line, it was going into a derivative. Same idea here. It's that same kind of number line. It's still a derivative sign chart. So whenever you use the number line, it has to go into the derivative, whatever you're plugging in. If you want to consider where the global max is actually at, that's where you need to use the regular function. For the quiz, it's going to be similar to just, here's a function on an interval, find the global max or min. You're not going to have to do all the hoopla from problem 5 that we did the other day. It's just, here's a function, here's the interval, find them. Any more questions or concerns before we head over to chapter 5? All right, I'll hold on for a couple more seconds in case someone's still writing that down. I actually need to pull up chapter 5, so I should do that while I'm waiting. Come on, here we go. All right, I'm not seeing any more questions then, so we're gonna pop over to, never mind. When there is an interval, you always plug in the endpoint. So if your interval doesn't include an infinity, yes. If your interval includes an infinity, like in this case we have right here, that's still up. It was from 0 to infinity. So if one of the endpoints is an infinity, then you need the number line. But if they're both numbers, then yes, you always plug the endpoints into the original function to compare y values. And there is an interval you plug in. Yeah. All right. Now I'm not seeing any more questions. So we'll pop over to just starting chapter 5. We won't get that far, but oh well. It's okay. So chapter 5. We're now no longer talking about derivatives. We're talking about something else that's somewhat related to derivatives, but not derivatives. So accumulated change and distance. I read that backwards. So suppose we're given the following velocity graph. So I know that number might be, well, don't thank God too fast, Caleb. Anyway, I'm just kidding. No, I'm not. Anyway, I'm gonna shut up. 5. So say we're given the following velocity graph. So essentially we have something that's traveling at a constant velocity of 15. Let's go ahead and say that this is in miles. Let me make that thinner. Go ahead and say that this is in miles per hour. So we got something that's traveling a constant 15 miles an hour. And I want to know how far they've traveled in the first 10 hours in this situation. Well, in general, how do you find how far someone's traveled if you're given a velocity? Well, you can take distance is the rate times the time, where the rate in this case is the velocity. How fast are you going? So if you multiply how fast you're going over how long you're going that speed, you'll get how far you went. So in this case, if I'm traveling for 10 hours at 15 miles an hour, we're going to have that the distance is 15 miles per hour times 10 hours, so 150 miles. Now, notice, I'll slow down a little because people are writing things down. Excuse me. So, notice that if I consider this graph and try to see where that's actually represented graphically, you might think it doesn't show up, but it actually kind of does in a weird way. So think about this. So we're cutting this off at 10 hours. So, you know, here we've got a length of 10, and here we've got a length of 15. Well, if I multiply those two numbers together, which is exactly what I did over here, that also technically finds the area of kind of this rectangle that graph forms. That is not a coincidence. That's kind of the point that we're going to lead up to. The distance that we just found is actually represented in that graph as the area underneath of that velocity function. And I think it's easy enough to see here because it's a rectangle. So if we go for 10 hours at 15 miles an hour, we just have this box. 10 times 15 would give us 150. So like the 150 is kind of appearing in here as our area. So hold on a second. So what if instead of that, let me try to keep as much of it in there as possible. What if instead of looking as just that generic thing, that constant velocity, what if the velocity function now looked like this, where we're going, this is some magical thing that can jump velocities in a millisecond. That's going 6 miles per hour in kind of this first 5 hours, so 6 miles per hour for 5 hours, but then it jumps up to 10 miles per hour. What if I wanted to figure out the distance that it's traveled in this situation? Well, again, I can kind of consider it here. I kind of have two separate pieces I can consider. I can kind of consider the distance in that first half as 6 miles per hour times 5 hours. So they must have gone 30 miles in that first 5 hours. But then for the last 5 hours, they're going at 10 miles per hour. So they must have traveled 50 miles. So how far did they travel in total? Well, they traveled the 30 plus the 50, so 80 miles. And so again, if we consider kind of the area of these boxes that this graph creates, we have that the 30 essentially appears as the area of that first thing, and the 50 is going to appear as the area of the second thing. And if we add both of those areas together, we'll get the distances that we travel. So hold on a second because people are writing. Ooh, no, that's not good. So what if instead of kind of these constant velocities, what if we said that we were, forgot to turn the pen off. What if we said that we were traveling at a, so sorry, I forgot I put this little question here. So what relationship do you notice between the distance traveled and the graph? It's the area, so distance traveled is equivalent to the area under the graph. The graph of velocity, maybe I'll say. And maybe I'll spell velocity right. So those distances kind of showed up on the graph as an area. So what if instead of a constant velocity, or even like a constant velocity in one piece and a constant velocity in another piece, what if we say that our velocity is a function of time, so it's some 5x, so you're speeding up over time, and that's your velocity. Well, I still wanted to find the distance that I've traveled in those first 10 hours. Well, in this situation, we cut this off at 10. Well, pretend that let me say we cut it off at 10. So here we don't have a nice rate times time because the rate is changing at every single second. So it's not like we can just take the velocity times time because the velocity is changing. But if we think about it in terms of area, if I can find this area, I can find the distance that I traveled, because that's what I just found. I just found that the distance traveled is equivalent to the area underneath of the graph. Well, in this case, that's a shape that I know. That's a triangle. So since we have a triangle, we know the, well, hopefully know the area of a triangle. So area of a triangle is 1/2 base times height, if you need a reminder. That's a 2. Doesn't look like it. So we could say that the distance traveled is going to be that area. So we have 10 and 50 as our base and our height. So 1/2 times 10 times 50 will be 250. So we know that over those 10 hours, this, whatever the heck this object is, would have traveled 250 miles. Cool. I'll hold on for a second. Well, too bad. Because I'm about to, well, we're not going to get to an example today, but I'm going to show you what we're going to do, because it's not going to stay that easy. What if we have a graph that doesn't have a nice shape to it? I'll wait like 5 more seconds before I scroll down. So I'll kind of present the idea of what we're going to do in this chapter, and then we'll be out of time, so we'll take our pick. But what if we don't have a nice shape to the function? And I'm going to kind of do 2 situations here. I'm going to try to draw the same graph, but, you know, I'm human. So say we have, you know, a graph, and pretend they're the same exact graph. And I break this up into like 5 sections. Those aren't very even. And pretend these sections are as even as I can make them. So say I wanted to consider, you know, the velocity, say this is still a velocity function, and say I wanted to find, you know, all this area in here. Well, I don't know the area of that shape. It's not a nice shape that we know from geometry. So what we're going to be able to do is we're going to be able to break these things up and estimate the area using shapes that we do know. Something nice, like a rectangle. So notice that I split the graph up into kind of, well, I split the x-axis up into a couple of pieces. Let me mark all of the y values at those pieces really quick. So what we're going to do, I'm going to write this up here. We're going to use known shapes. And in our case, we're going to use rectangles. In some situations where you talk about this a bit more, you can get into different shapes, specifically trapezoids. But, meh, So we're going to use known shapes to estimate the area. So essentially what's going to happen, and again, we're just going to be able to talk about what we're going to do, and then on Friday we'll see an actual example of how we're going to do it. Now there's kind of two ways we could do this, and that's why I have the same graph to the best of my ability in both cases. So notice I'm kind of splitting these graphs up into these sections. Now, if I want to use rectangles, I need a width and a length, or a length and a width, or a length and a height, whatever you want to call it. Well, I've got some, I think we usually refer to these ones as the width. We've got some widths going on, just from how I split these up. But where am I going to find the lengths from? Well, the lengths are going to come from the height of the function, but what height of the function do I use between those 2 points? And this is kind of where we get kind of two situations. Let me do this in a different color, and let me make it a little larger so that there we go. So notice that in kind of, if you treat these sections as like an interval, you kind of have like a left side and a right side, right? So we're going to choose either the left side or the right side to use the value of the function. So say I wanted to use the right side, and I didn't change the color apparently. Say I wanted to use the right side. So we're going to have two different types of estimations. We're going to have a right side and a left side. So what that means is I have like this kind of first interval here between 0 and say that's 1. Say all of these pieces are going up by 1. So if I want to choose the right side, I choose the height of the function at the right side of that piece. And then in my next piece, I choose the right endpoint, and I use that as my height. And I choose the right endpoint, and I use that as my height. And I choose the right endpoint, and I use that as my height. And in this last interval, I choose that point on the right, and I use that height for my interval. So notice that there's some area above the graph that we pick up and some area below the graph that we don't get. These are estimates, and this is the best we can do at this point because, again, we don't know the shape of that graph. It's not, it's not a shape that we know how to take the area of. So the best thing we can do is break it up like this and estimate it using areas we can actually find. Who comes up with this stuff? Leibniz and Newton. That's who. Now, the other way you can do it is you can choose the left point instead. So notice in the right case, there was this point out here that I never used. Notice it's the only one still in black and not covered up by the blue. I could also choose what we call the left side. Left. Left. And that's doing that same idea of viewing it as a kind of interval, but we're taking the left side as our height, and the left side as our height, and the left, and the left, and the left. And notice there's one point at the very end on the right that's not used. So essentially, we're thinking of breaking these graphs up into little tiny pieces, and we have our width, however we're breaking it up, and we're finding these lengths of these rectangles by using the function at either the right side of the interval or the left side of the interval that we're breaking it up into. Again, we'll get into actual examples of this on Friday. We're out of time, but that's the idea that we're doing here is we're estimating areas underneath of functions using rectangles. And the reason we're doing that is notice, so we were starting to talk about it with velocity, where we could find distance traveled with the area. That's going to happen in generic situations too. If we have a rate, we're going to find a total amount of change as that area. So that's what we're going to be focusing on in chapter 5. But we'll come back to that on Friday. It's time to take our quiz. So if you're on Teams, I'm going to stop the recording. Please. I'll take you off the big